Good afternoon, everyone. So we're going to start a new unit today, and this unit is exciting in the sense that it has a completely different way to approach classification and regression than what we've seen until now, and it works very well. So let's start to dig in. So we're going to be talking about two very different ideas today, and then we'll combine them at the end. So the first thing we're going to talk about is called ensembling or ensemble methods. And then later we'll switch to decision trees. And so let's just start at the beginning. Have you guys heard of the wisdom of the crowd? That the notion that when you have a lot of people, like their individual predictions or opinions might be faulty, but when you combine them, you can come up with a much better answer. So one example of this could be, let's say that there's a coin that's biased. It has one side, and let's say we don't know this, but heads occurs 70% of the time and tails occurs 30% of the time. And let's say that our objective is simply to figure out which of the sides of the coin is biased. We're not trying to figure out the percentage, we're just trying to say, is it heads or tails? So it's a binary classification type problem, right? And let's say that our method is simple as this. We're going to flip the coin n times, and we're going to choose the majority vote. That's going to give us that binary outcome, right? And let's think about the effect of n, how many times we flip it. So if we flip it once, well, because heads, which is the correct one, occurs 70% of the time, we're going to be correct 70% of the time. Right? But if I flip it 11 times, and then I'm going to choose the majority vote out of those 11 times, it's not too difficult to prove that it's going to be correct 92% of the time. This comes from the CDF, the binomial distribution, which sort of counts all the different ways that those 11 flips can turn out and how often each of those ways turns out. And then if you go and flip it 21 times and take the majority vote, now you're going to be correct 97% of the time. If you do it 31 times, you're going to be correct 99% of the time. And so you can see how each coin flip is like a really faulty measure, very inexact, measure of which is the heavier side. But then if you can actually combine a number of them together in a smart way, it does much better. You can really figure out. So that's the kind of just a tangible example. And then we can apply exactly this idea to binary classifiers because, like I said, this is really a binary classification problem where it's like each classifier is correct only 70% of the time. So if I have 31 binary classifiers, each correct only 70% of the time, and I do this majority vote idea, I can get 99% accuracy, right? Which is way better than any of my binary classifiers. So that's kind of the potential that we are hoping for in using these methods, applying these methods to machine learning. And some important terminology here. When we talk about doing this, these binary classifiers are these are what we call weak learners. They're just weak because they're not very strong. But then when you put them together through this majority vote, that's how we make what's called a strong learner. Okay, so the strong learner is basically just this approach, and we call this overall procedure ensembling. An ensemble is just like a collection of things, and then ensembling is putting them together in this way. And there's different ways to ensemble, which we're going to talk about. This is just one way, this majority vote. There's better ways. But we have made a big assumption in taking our coin flip idea and saying that it relates to classification. And the big assumption is that in the case of the coin flips, every time you flip the coin, it's an IID realization of this random variable, right? Every coin flip is independent of the others, and each of those coin flips follows the distribution of the coin itself. When we do it with classifiers, it's not clear exactly that if I have 31 different binary classifiers, that they're somehow going to be independent. In fact, it's not clearly going to be different at all, right? If I have identical classifiers and I feed them identical data set, it's going to be the same thing 31 times in a row, and it's not going to help me to do any of this, right? So the key in making this work for us is to somehow make sure that those weak learners are sufficiently diverse, they're sufficiently different, that you see the gains of ensemble. Okay, so we're going to talk about how to do that. All right. Everybody good so far? The ideas? Okay. So, so we're going to focus on classifiers for the moment, but actually nothing is really very specific to classification. We can do all these things with regression as well. So some of the basic methods, if you're given a collection or ensemble of base classifiers, these would be like your weak learners. Then the hard voting classifier is the thing we talked about on the previous page. You take a majority vote of hard decisions. So if we're talking about binary classifiers, each one is a 0 or 1, and you have to combine the zeros and ones. You just take the majority vote, and that gives you another binary 0 or 1. Something that works better is if you have a classifier that can generate a soft output. So by a soft output, we mean, for the binary case, this would be a probability between 0 and 1. As we know with, let's say, logistic regression, we get that at the output of the sigmoid. Or if we train a neural network for classification, we can get that at the output of the sigmoid. So if you somehow have that soft information, the soft voting classifier just takes an average of the soft information of all your classifiers, gives you another soft variable between 0 and 1, and then finally you can quantize that. You can round that when you're done. Okay, so that's another approach if you have classifiers that give you soft outputs, and that usually works a little bit better than the hard voting classifier. Both of these options are implemented in scikit-learn's voting classifier method. Okay, and as we said before, the voting classifier will be better than the base classifiers if the base classifiers are sufficiently diverse, right? That's the key. If they're all doing the same thing, you won't really get any gain. But if they're doing different things, you get an improvement. So at the highest level, there's sort of two ways that you can imagine introducing diversity into your base learners. So one way is you use the same classification method or function for the classifier in all cases, but you feed it with different data sets. So for example, the simplest way is if I have 10 base classifiers, I take my full data set, I shuffle it, I split it into 10 parts, I give each part to one classifier. Right? And now they have less data to work with, but they'll be independent. Another approach is you use a common data set for all the classifiers, but you make them structurally different. So for example, maybe the first one is a logistic regression, the second one SVM, third one neural net. And so now you hope that they behave in sufficiently different ways that they give you different answers and you can somehow, it helps to combine them. So those are sort of at the high level, two different ways you can do this. But there's even another way. Let's say you want to do, you're only going to use logistic regression for your classifier. What you could do is you could force your different logistic regression models to only use random subsets of features. So now you're sort of forcing them to behave differently in that way. That doesn't always make sense, but it might make sense if there's tons and tons of features and you know that the information is sort of spread across the features, and so it doesn't hurt you terribly to remove a bunch of features. If you just had very few features, that'd be a bad idea, but if you have lots, maybe you can do this. Okay, so those are sort of at the high level. Two different ways to get diversity, different data sets, different prediction models, and you can actually combine them too. Any questions so far? Okay, and all the stuff we talked about, you can do this with base regressors. You wouldn't have this hard decision thing, but you could just average their outputs. Yes?
One example of remove features that we have a lot of that we can remove would be that lab we did on the brains.
The ECG, yeah. Yeah, that would be a good example, right? Mhm. Okay. So let's zoom into this data diversity idea here. Talk a little bit more about that. So for data diversity, there's sort of two kind of well-known ways to go. The first one is what I described earlier. It has the name pasting, and it's basically drawing samples I from your full data set without replacement. So that means like you have a full data set of n samples, you pull out one sample, give it to one predictor, and now that sample is not available for anyone else to use. So you didn't replace it. So in that case, each sample in your data set is used exactly once by one of the predictors. Another approach is called bagging, short for bootstrap aggregating, but everyone calls it bagging, is to draw samples with replacement. So it's kind of a weird idea. You take the sample out, you give it to your first predictor, and now you just replace it in the data set. Now you go and you take another sample out, maybe you give it another sample to the first predictor. It may actually be the same one. So it's kind of weird because now it has this redundant information, right? And in fact, there's going to be some samples that maybe never get picked for any predictor. So it sounds kind of weird, but actually it usually works better than pasting. So with bagging, some more details. So typically, if your data set has size n, you usually draw n samples for each predictor. And you can do an analysis that shows when n is large, 37% or precisely e to the power minus 1 samples, percent of the samples will go unused per predictor. Okay, so like the first predictor gets to see essentially 63% of the samples, and then within it, 37 are redundant. Second predictor has another 63% of the original data samples, but it's going to be different. It's going to have some overlap with the first predictor, but some that won't overlap, and so on. Another nice thing you can do now is for each predictor, there's the samples you never use for it. They call those out-of-bag samples. You can actually use those for cross-validation to see how well that predictor is doing. So they're not necessarily going wasted. Okay, and bagging works extremely well, and so generally works better than pasting, so that's what people use. Maybe part of the intuition there is that with pasting, if I have, let's say, 10 different predictors, each one would only get 1/10 of the data set, which is not many. But with bagging, if I give each predictor n samples, then each one would get 63% of the data set rather than 10%. So it would have a lot more to work with. Okay. So these things are implemented in scikit-learn's bagging classifier and bagging regressor. And you just choose the bootstrap variable true for bagging or false for pasting. And if you want it to report the out-of-bag cross-validation, you just do OOB score equals true. And it will give you that information. Okay, so that's different ways to introduce data diversity among these different base predictors. Any questions? Okay. So now let's talk about that random feature idea, which we said is another way to introduce diversity by structurally preventing all features being used by all predictors. So as we said, it might be useful when features are high dimensional and somewhat redundant. And so now you can do this sampling idea like this. You can sample with replacement or without replacement, but over features. So those are typical options, bootstrap or not. And in fact, you can combine random subsets of features with data diversity, do both at the same time, and then there's these particular this particular terminology. So when you use both random data and random features, that's called random patches. And when you give the full data to all the different predictors, but you use random features for each predictor, that's called random subspaces. Okay, and these things are implemented in the same bagging classifier, bagging regressor. And to do this, to do feature randomization, you just set max features less than D, where D is the total number of features you have. And if you want to do bootstrapping, you just do bootstrap features equals true, and that does this sampling with replacement. Okay, so it has all these options there for you. Okay, all right. Any questions? Okay, just going through all these options. So now we're going to switch gears, and we're going to talk about decision trees, which is a very generic way to do either classification or regression. And as you'll see, it's very different than what we've talked about so far, but it's very powerful in its own way. So we can, in fact, talk about regression and classification at the same time in this case. We're going to set things up as usual, where we have feature vectors xi. We'll just assume for now that our labels are scalar, but if we want to do vector labels, we can do that as well. And so these labels, they could be categorical for classification, or they could be ordinal for regression. But basically, decision trees, you can think about it as a two-step approach. You first partition your feature domain, which is RD, because we were assuming we have D features. You partition that into capital L regions. So for example, down here, if I have two features, x1 and x2, you can see that the space of features is chopped up into these rectangles. So this is just kind of looking down from above. You would see like this region here corresponds to this region in the x1, x2 plane, and so on. And so assume that you know how to partition into these regions. So anytime the x you use at test time, when that x comes in and you want to make a prediction, anytime that is in the little lth region, you output the number ZL. So ZL are some learned things, and these regions are also things you've learned. But essentially, you just learn how to set up these regions, and for each region, you just use one scalar output. So that's illustrated here on the left. So like Z would be the output, and you can see whenever X, the features are in this region, you output that level of Z. Whenever you're here, you output this level of Z. Whenever you're in this region, you output this level of Z, and so on. So that's it. It's kind of like lookup table, you could say, right? It's like you figure out which region of the input space you're in, and then you just look up the output for that region. So that's it. Of course, the interesting thing is how do you determine the region and how do you determine the outputs? We'll talk about that next. Is that overall idea kind of making sense, or? I see some furrowed brows. Yeah.
Would it make sense to, instead of just outputting a fixed ZL, have that also be learned?
Oh, it is learned.
Oh, okay.
Yeah.
Yeah, but
What's learned are the ZLs
Yeah.
and the regions themselves. You learn those.
But like, could there, like, is ZL a function of x1 and x2 within the region?
No. No, this is just, this is the nature of trees. You don't really need that because you can make your regions as small as you want, as fine as you want, right, to have as much precision as you want.
Wouldn't that introduce overfitting then?
Yes.
Okay.
Yeah. So that is something we're going to have to figure out how to deal with. But yeah, this is just how trees work. They're done this way for simplicity. But yeah, getting them to not overfit is something we need to think about later. Okay. Okay, but is the idea of how they work, is that clear? Are there some more questions? Okay. So just as an example of how you might decide to set the ZLs, let's say we're talking about regression. And so what I could do is I have a training data set, and if I want to figure out like this value here, I could look at my training data, and I could collect all the training samples that land in that region. So that would be the set SL. Those are all the indices I for which XI is in, let's say, region 1. And now, for each of those, I look at their labels, So now I have a collection of labels, and I might just compute the sample mean of all those labels, right? So for all my training data, I just take the average label of all the labels that ended up here. And then, I have a different region here. That will give me a different subset of indices, a different sample mean, and that will be the value that I use for Z there, and so on. If I'm doing classification, I can't use the sample mean because I need my classifier. If this is a hard output classifier, I need it to output, like if it's binary 0, 1, I need it to output either 0 or 1. I can't compute a mean because that would be somewhere between 0 and 1. So I might instead look at the sample mode, which is the most common value among the training labels whose training feature vectors all landed in that region. Okay, so I use sample mode instead of sample mean. But just give you an intuition about how you could set the Z's once you determine what these regions are. Okay, all right. Any more questions on this? Okay, so why are these called trees? What is tree-like about this, right? I don't see any trees. So the tree aspect is connected to another simplification that's made in this idea is that you construct the regions just by thresholding one feature at a time. So for example, and that gives you a decision tree. Okay, so here's an example. So let's say we have two features, x1 and x2. And so what I do when I receive a new x1, I first say, is that x1 greater or less than the threshold t1, which is this number here on this axis. So if x is less than t1, that puts me over here, and I go down this branch of the decision tree. On the other hand, if x1 is greater than that threshold, that means I'm going down this branch, which means that I'm over here. So I've kind of partitioned the data, you could say, into two big regions. But I'm not done yet. I could furthermore, if I'm in this region, I could furthermore say, well, let's now look at x2, the other variable, and decide whether, or partition it based on whether that is less than or equal to t2 or not. So that will split that region into these two subregions. Okay. And I'm doing that by just looking at x1 alone, by looking at x2 alone. And so as you can see, what will this force about the regions? If we do this, the regions will have what shape? Rectangles whose edges are perpendicular to the coordinate axes. So in principle you could say, well, I want to build decision regions with kinds of crazy shapes, and yeah, you could do that. It would just be hard to implement. So to make the implementation really easy, we're going to say that's not allowed. We're just going to only threshold each feature one at a time, and that's going to give us these rectangular decision regions, and that's just a choice for simplicity. And again, it's not really that much of a limitation because given any training data set, I can always figure out how to chop it up perfectly just with even these rectangles to where I can predict everything in that training set perfectly, right? So it's not really limited at the end of the day by these design decisions. You can still like perfectly categorize any training data set or perfectly predict it. But of course, the problem then is going to be overfitting, as we know. It's like, that's not necessarily a good thing to get zero training error because maybe your test error won't be zero. Okay, so that's the idea. That's why I call them decision trees, and that enforces this particular structure on our decision boundaries. So some more terminology. When you talk about the very first decision you make, that we call that the root of this tree, and then the final edges here of the tree, we call those the leaves of the tree. And we use L, the number of regions, that basically tells us how many leaves we have. So in this case, we have 5 leaves. Each leaf tells us a particular region. Okay, so here we have 2 features, 5 leaves. Okay. All right. Any questions on this? All right. So now let's talk a little bit more about how we're going to do this training. So typically these decision trees are trained in a top-down manner, which basically means you start here, you first learn this first feature, then you go and then you learn this one, and then you learn this one, and so on. And every time, yeah. As you do that, you finally come up with all your regions, and then once we know our regions, we could do this sort of learning of the outputs per region. Okay. So how do we do this learning of the thresholds of the regions? So the main idea is we're gonna do recursive splitting. So at the root of the tree, we're gonna split our data into two parts, S1 and S2. So this is how we're gonna try to design T1. That's gonna split into those things, right, or this versus this. So all the data, all the training samples that land here, we're going to call them, or that subset of indices, we're going to call that S1, and all those that land here, we're going to call that S2. And this is how it works. We want to choose that split so that the labels are most homogeneous, the most similar after we made the split. So we want the labels within here to look similar to each other, and we want the labels here to look similar to each other. And we're going to move this T around. We'll hypothesize different T's and then evaluate the homogeneity for the different T's until we find the best T, the most homogeneous here and most homogeneous here. Okay, so for example, one decision we have to make, first of all, at this level, is which of our different features we're actually going to threshold, right? So that we could call that choice J indexing the feature. So I have to choose, first of all, am I going to threshold feature 1 or am I going to threshold feature 2? And for each of those choices, I have to figure out what is the value of the threshold as well. Those are 2 things I have to figure out. So essentially, you would go through all the different features one at a time, and for each feature, you have to figure out the threshold. So first you have to ask yourself, is this an ordinal feature or is it a categorical feature? Trees can handle both of them, no problem. So if it's an ordinal feature, then it's just a matter of choosing a real number threshold T. So, and the choices are somewhat limited because you have n data samples, right? So, and if you just order your data samples, for that particular feature, you can put a threshold here, 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 here. So there's a finite number of thresholds to consider, basically. So it's not like you have an uncountably infinite number of T's to think about, just a finite number of possible T's. So you would go through and you would, first you'd say, let's hypothesize I do J equals 1. Let's hypothesize all those different thresholds, and you would measure the homogeneity for each choice. And then finally, you say, okay, this was the most homogeneous. And we'll talk about exactly how we measure homogeneity in just a moment. Now, if we had a categorical feature, we have to do it a little bit differently. So imagine that this feature had 4 categories, A, B, C, D. And so we have to think about, there's, again, a finite number of ways you can split up those 4 categories. So maybe we're going to threshold, or we're going to split our data if that feature is in categories A, C versus B, D. That's just one way you could do it. But there's a finite number of different ways to split up with those 4 categories. So you just try the different ways and then see which works best. Okay, so that's essentially what we do. Once you've decided at this level of the tree, you've decided I'm going to use feature 1 here, I'm going to use this threshold. Great, now your data is split into 2, and now you repeat. Now for this subset of the data, you split that further up into 2 more. And you have to choose again, now which feature, now which threshold. Okay, so that's this top-down induction. It's just this recursive procedure. And it goes until, at some point, you have to stop, right? So there's different ways to think about stopping. So one way that you would stop is if you find that all the labels here are identical, perfectly homogeneous. There's nothing more to do, right, at that point. Basically, it's like saying your training data says that there's one right thing to report here. It's exactly that label. You don't want to report anything different according to your training data. So that would be a good place to stop. Another thing you could do is you could say, well, I don't want to overfit. I'm worried about overfitting. So I'm just going to say I'm going to have a maximum depth. I will only split 3 levels, no more. Or you might say, I never want the number of samples in each one of these regions to fall below 10. I just want to have at least 10 samples per region. So those are common ways of stopping. Minimum number of samples, max depth, and so on. Or labels are perfectly homogeneous. But that's how we do it. Consider one split at a time until we're done. Okay. Any questions? All right, let's do an example. So in this example, we're going to design a decision tree for an insurance problem where we have 2 features, which is the age of the driver and the car type of the driver. And the label, we're trying to predict whether that driver is going to be high risk or low risk. And this is our training data. We have 6 training samples. You can see various ages, various car types, various labels. So let's maybe imagine, at the first level, we have to first decide, are we going to split according to age or are we going to split according to car type? That's which feature are we going to split according to? Let's consider splitting by age. And to make that make more sense, let's rewrite things where the ages are ordered. So I'll just write it up here. So we have 17 is our youngest driver. Then we have a 20-year-old, 23-year-old, 32-year-old, 43-year-old, and 68 years old. And then now, remember we care about homogeneity of the labels. So let's write what the labels are for these different drivers. So we have high risk, high risk, high risk. 32-year-old is low risk, high risk, low risk. Okay, so now if we're going to split according to age, we have to figure out what threshold to use that's going to make the 2 subsets most homogeneous. So what do you think is going to be the threshold we want to use? So we basically have 1, 2, 3, 4, 5 different possibilities of threshold, right? If I put the threshold here, that's kind of trivial because there's no samples here. If I put the threshold here. So I have 5 choices of threshold, essentially. Which one?
After 23.
After 23. Yeah, because if we do it this way, this is perfectly homogeneous, and this is almost perfectly homogeneous, right? So that's pretty much where we want to be. And if we need to come up with a very specific number, we could just look exactly halfway between 23 and 32, and that would be 27.5. So we could also evaluate doing this with car type. I won't go through the details, but if we compared splitting versus car type or splitting versus age, let's just say age turns out better. So that's what we're going to split at the first level, and we're going to use 27.5. So now I've split my data into these 2 subsets. So now let's consider left of here. Do I want to split this anymore? No, perfectly homogeneous. We can perfectly predict the risk of any driver that's less than 27.5 years old, right? High risk, according to our training data, right? Sure, there's some safe drivers out there, but according to our training data, no. Okay, but if I look at this other subset, we have more work to do. So for this other subset, we might consider, again, splitting versus age, so you would either split there or there. But in either case, you can see that I would not have something that's perfectly homogeneous. I would either have this or I have this after one split. So let's instead think, is it better to split versus car type? So for that, let's write the car type above it. So for the 32-year-old, we have a truck. For the 43-year-old, we have a sports car. Looks like maybe a midlife crisis vehicle. And then for the 68-year-old, we have a family car. Okay, so now if I split according to the category, can we get a perfectly homogeneous split? Yes. So how would I do that?
Sports versus non-sports.
Sports versus not sports, exactly. Sports is high, not sports is low. Okay, and that's essentially what we're doing here. And at this point, each of these is totally pure, so there's really no justification to split any further, and we have our tree. Okay, so that's essentially how we train these models. Any questions? Okay. All right, so let's talk about homogeneity metrics for regression. Remember, our goal is to maximize the homogeneity or the similarity within S1 and S2, or minimize the inhomogeneity, or let's say diversity within those subsets. So if we're talking about regression, our labels would be ordinal, let's say real numbers. And so we could measure inhomogeneity or diversity by the variance you get after the split, right? That how much it deviates from its mean. That's one way to do it. So since we're considering taking the full data set and splitting it into S1 and S2, the way we would do this is we'd first compute the sample mean of each of the subsets. So we would have a mu1 for the sample mean for subset 1 and mu2, sample mean for subset 2. Now that I have the sample means, I can compute the sample variance for the two subsets. So here's my sample mean. I'm just looking at the average deviation from the mean. So I have these two sample variances. But I really need an overall measure of the split. So I can't have two numbers, I need to combine them. So one way to combine them is to do an averaging of those two variances, but I'm going to do a weighted average where I'm going to weight by the size of subset 1, the ratio of how many samples are in subset 1 versus how many are in subset 2. So the bigger subset, I'm going to weight that variance more. And that gives an overall variance after the split. And so now for every hypothesized threshold t, I could compute the variance, and I would finally figure out which is the t that gives the minimum variance, minimize inhomogeneity. So that's one option. Yeah.
Why would you weight the bigger subset more? Because it seems like it would have more variance being larger, so it would, I don't know, I would just think it would make it less.
Well, then, what if I would just come up with a subset of size 1, which is perfectly homogeneous, and then the rest is n minus 1. And now if I'm looking at the minimum one, I'm done, right? So that would not work. Yeah. So I guess intuitively, like, the bigger subset matters more, like, right? If that has a high variance, there's more samples in there, it's more meaningful. Okay. So another option, if you don't want to use variance, you could use absolute error. It's, just remove the square, just absolute value. Absolute error is known to be more robust to outliers than the mean squared error, so that would be maybe why you do that. And when we discuss XGBoost on Wednesday, we'll see that there's a more sophisticated metric you could also use. these are sort of things you could do for regression. Variance, absolute error, things like that. Okay, any questions? Okay. Now if we're doing classification, it's a little bit more complicated. So imagine that we're doing classification among capital K different classes. So our labels are integers from 1 to k. So now we need to consider, for this little elf subset, we need to consider the empirical label PMF. So this is a vector or a collection for fixed L, but as you range over this little k, maybe I'll draw a picture, it's something like this. Maybe I have classes 1, 2, ... to k. And these numbers here, these numbers are in the interval between 0 and 1. And they're just telling us for these samples, like what percentage of the samples are in class 1, what percentage are in class 2, and so on. So, these all need to be non-negative, and when you sum them up, they have to give you 1. Right, so this is just empirical label PMF. That's what we call it. This is the equation that generates that. This is our indicator function. It takes on the value 1 when yi equals k. Otherwise, it takes on the value 0. So they're just counting up your samples to make this PMF. Okay. And so now we want to measure inhomogeneity. For each split, you're going to get one of these PMFs for S1, another one of these PMFs for S2. And one way we can look, and this is the same kind of weighted average of something called the Gini impurity, which is one of the most popular metrics here. So this is the sort of weighted average we saw for variance on the previous page. So we need to compute the Gini impurity for our two different subsets. And the Gini impurity looks like this. It's 1 minus the sum over the different classes of the squared values in the PMF. Okay, so let's try to make some sense of this. What would be the case where I have the most homogeneous S1? So let's say I have a bag of marbles. Each marble is labeled with 1 through k. How do I make that bag most homogeneous? Give me an example. Purely homogeneous bag would be all ones on the marbles or all twos, right? What would the PMF look like for any of these cases? Impulse. So it means that all of them are in 1. That's right. They're all taking on set 3. So yeah. So in the case of perfectly pure, you get an impulse. And in fact, what is the height of that value here? 1. Okay. So let's plug that in. So I'm going to sum up the squared values. So I'm going to 0 squared, 0 squared, 1 squared, 0 squared, 0 squared. So when I sum this up, I'm going to get 1. 1 minus 1 is 0. So the smallest you can get, the most perfectly homogeneous case gives you a Gini impurity of 0. So that's the lowest. Can't get negative. Now what's the opposite case where you have the most diverse marbles? What would the PMF look like? Flat line, uniform, right? What's the height of each one of those bars then? 1 over k. So let's plug that in. 1 over k squared, but then I'm summing k of them. So overall, this is k times 1 over k squared. So 1 over k. So the largest this can get is 1 minus 1 over k. So those are the extremes between perfectly pure and maximally diverse. So that's how you can measure, one way to measure homogeneity or inhomogeneity for classification is this Gini impurity. There's many other ways. Entropy, misclassification error, chi-square. I'm not going to get into any details. If you're curious, you can look inside this book. They explain all that stuff. But just want to give you the basic concept of how you can do this for classification. Okay, so we've seen our homogeneity metrics. We've basically talked about everything. Let's just kind of step back and talk about the advantages and disadvantages of this decision tree approach. So advantages, first of all, these things are very general. We really made no assumptions on our data at all. It could have features that are categorical, ordinal. It can have labels that are categorical, ordinal, right? No problem. We don't even need to standardize the features, because if you standardize them, then all the decision boundaries would just change accordingly, right? It doesn't really affect anything at the end of the day. So you don't need to standardize when you work with trees. It should have no effect on the result at all. Also, trees are very interpretable. So for example, like, let's go back to our insurance problem. If you have a driver that says, like, why did you categorize me as high risk? It's unfair. And be like, well, I can tell you exactly why. It's all explained by this decision tree. There's no magic, no unfairness. This is how we came up with the rule. So it's like, for legally, this is great. For anything where there's like legal implications about fairness or anything, decision trees are great for that. Because otherwise, if you do this with a neural network and someone explains, why did your network come up with this? You'd be like, I have no idea. Right? And it's actually a big issue. And there's a lot of applications where you can't use neural networks because legally, you can't explain why you came up with that decision. And there's laws that say you need to be able to do that. So that happens in the insurance agency, lending, things like that. So they're what we call a white box model, which is the opposite of a black box model. Basically, we can understand exactly how we arrived at this prediction. Also, the prediction is pretty fast. So people say it's on the order of log base 2n. The reason, or the way you can think about log base 2n is, imagine that you're going through the decision tree, and at each stage, you split your data set in half. So if I split it in half after one stage, 2 stages, I split those in half, and so on. By the time I go through log base 2n stages, all my leaves have 1 sample in them. I can't split anymore. Okay, so now your splitting doesn't always work out exactly half, 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 but it happens, roughly speaking, it's on the order of that many stages in your tree to process a data set of size n. So that's how many decisions you need to process a test sample super fast. Okay, those are the advantages. Disadvantages are as follows. The training can be expensive, especially if you have to consider all the features at every split, and there's a lot of features, right? That just takes very laborious. But so the solution that people usually use is they restrict to a few randomly chosen features at each split. So they say, I'm only going to look at 1, 10, and 51. I'm going to choose those randomly and only consider those at this split. And another reason why that works well is because trees are prone to overfitting. If you don't put any restrictions on them and you go until, as far as you can go with the tree, you will perfectly predict all your training samples. That's not necessarily a good thing. So if you do things like restrict, to certain random features at every split, it actually helps a lot with the overfitting, as well as make them train faster. And there's other things you can do to help them not overfit. You could, enforce a minimum number of samples per region. You could enforce a maximum depth, and so on. There's a really nice overview of decision trees in sklearn if you want to see, more of a textbook style discussion of them. Okay, so that's decision trees, and then we learned about ensembling. And so decision trees on their own are not used that much precisely because of this overfitting issue. It's kind of a little bit challenging, to deal with the overfitting when you just have one tree. But what works incredibly well is when you have many trees in an ensemble. And that's what random forests are. So decision trees, they tend to overfit, which means they have low bias and high variance. But that's exactly what you want in ensembling. You want that the variance is high. That means they're different. So when you ensemble them, you actually see the gains. But you also want them to be unbiased, because if you have like a whole bunch of weak learners that are all biased the same way, then even if they're diverse, when you average over them, the result is biased in the wrong way, right? So you actually want techniques that have low bias and high variance. They're ideal for this application. So that's where random forests come from. You have an ensemble of trees, and what you do is for each tree, you use a random subset of data. You could do this with bagging or pasting, and you could consider a random subset of features at every split for a given tree. So that will speed up the training and encourage further diversity. And so this is implemented in scikit-learn, random forest classifier, and regressor. The default settings work really well, so when you try this with real data, just out of the box, you get a pretty good prediction without messing with it at all. Here's just sort of a visualization of a particular data set, a two-dimensional data set. You can see that this is the half moons data set. There's basically, roughly speaking, like the data for the two classes look like that. Of course, it's kind of, it's difficult. There's overlap and so on. So with tree zero, the way it was trained with a particular subset of data samples and random features and so on, as you can see, these are the decision boundaries that came up with, or not decision boundaries, the regions that came up with. There's some weird ones, like there's this little blue one sandwiched in there between the pink, but whatever, that's what it came up with. Tree 1, as you can see, quite different. Tree 2, again, quite different. Tree 3, quite different. Tree 4, quite different. But then, when you average them, you get this, which looks quite a bit like the underlying data set. It has a nice boundary that looks, something like that. So it's just an example. Typically, when you do this, you might work with like 100 trees, on that order. Of course, it depends. It's definitely something you can tweak and try different values for, but it works well. There's a nice overview in this link about all this stuff, but it's in sklearn, random forest classifier, and regressor. So that's enough for today. Next time, we're going to talk about slightly different way where instead of training trees in parallel, we're going to actually train them in series. We'll train one, we'll look at how well it's doing, look where its errors are, then we'll train another one that's kind of trying to correct the errors from the first, and then we'll train another one that's trying to correct the errors from the second, and so on, and then we will combine all those guys together to make our strong learner. So that's what we'll talk about next time. Any questions on? Yes?
Curiosity, would it even make sense to try to use a random tree as a layer in a deep network? Would there be any, or do they pretty much need to be
It's a good question. Does anybody have any? I can think of one answer. Why? Anybody? Why wouldn't we want to use trees in a deep network?
Would it break back propagation?
Yeah. How do you back propagate? Right. It's the decision process or the training process for trees is very different. So I think that would be my answer. I don't know how you back propagate through it.
Sure. I think that makes sense. I was just curious.
Yeah. All right. See you guys on Wednesday. Yeah.
I found that I can't open the data for an Eclipse. I cannot find this one.
Okay.
So I can't do random train.
Oh yeah. These links never worked.
So how can I get the train and the data?
So you look at the Flickr demo in the course website. All of our demos have always been in the same place.
Demo
Yeah.
I can't, why would I do it again?
There's 4 demos.
I was thinking of starting
Flickr one.
the Flickr is what we need to do my lab.
It's what?
So we use this one to do the lab now.
Yeah.
It would have been in the grad lab. And also where it was.
Hey, I have a quick question.
So on the last lab 8, I went ahead and tried to add GPU acceleration.
Okay.
I dropped my lunch.
I was curious, I got it working, but I was curious how you would go about adding multi-GPU acceleration.
20 minutes before.
I mean, it's It's all supported in PyTorch, so it's really just a matter of,
It was fine, I mean.
so there's kind of two cases. One is where the multiple GPUs are in the same server, and then there's another case where the multiple GPUs are actually distributed among different computers. And PyTorch,
Well, not so.
I believe it
like,
handles both
I
of
grabbed my
those,
sandwich
but
and then I left.
there
It
are
was like
some
I just
extra
knew people were
packages.
gonna
There's
be
something called
late, and I
PyTorch
wasn't
Lightning,
So I went to the
which my
library.
PhD students tells me
I realized
is
there I had lost my
better
stylus, so I
if you
walked
really
back
want
to
to
the
do stuff
ground,
across
got
different
my foot
machines.
forward, and I checked the fridge, there was
It basically
nothing.
takes all the crazy stuff in terms of like
I'm gonna ask
training
them
them individually, but then
questions,
somehow
I'll see if you go.
combining the back propagation results. It basically does all that for you. So, yeah, there's implementation details, like getting it to work is always
Yeah.
an issue, but, and it just really kind of depends on the platform you're working on, but it's all supported, so it's all
Okay.
there, yeah.
Yeah, okay, that makes sense. Yeah, I was like, I had trouble telling if it was even working. Like my CPU
Uh-huh.
usage, when it was just CPU bound, was like almost 100%.
Uh-huh.
And when I had everything configured, my CPU usage stayed in like 15% range, but my GPU
Yeah.
usage didn't go up like at all. So I was like,
Oh, right.
it's like,
Well, yeah, so there's like, I
I
guess
noticed
it's
it was talking
NVIDIA,
about-
probably,
yeah.
right? There's like, I'm trying to remember what the command is, it's like SMI, or something, there's a command that you can run on the command line which tells you what the GPUs
Oh,
are
okay.
doing, and it will like, it'll tell you, yeah, you can see when they're being used as numbers go up.
gotcha.
But when you train the model, the CPU is still doing all the data loader stuff.
Right.
So it definitely is very active, especially, you know, it has to do all the batching and all that.
Mhm.
And that can sometimes be the bottleneck, in
Okay.
fact. So, yeah.
Gotcha. Also, do you climb?
No, not really.
Not really?
No.
Okay. I saw the Black Diamond keychain. And like
Oh,
the
yeah,
climbing shoes.
no,
You
just
like
a
hike?
wannabe climber.
Oh. Alright.
No,
Thank you.
Yeah, see ya.
Just random question. There's an emeritus faculty, B. Chandra Sakaran. I don't know, have you ever interacted with him
At
at all?
Ohio State?
Yeah,
You
so
know what
I mean,
department?
EC. So, I mean, he would have, I think he actually became emeritus in like 95, so long
Yeah,
time
because
ago.
I was not here then.
Okay,
So I don't know.
Okay.
I've not heard of him, so.
not heard of him.
I
No,
don't know
it's-
if he's alive or
I
anything.
think so I was doing Easter celebrations over the weekend or whatever with my family, and I was talking with my dad, and actually my dad was, well, it was computer and information sciences
Yeah.
when he was here.
Right.
But that was his advisor, and
Okay,
like my father's research was the state of AI in 1970, right?
Yeah.
But I mean, like we talked about all these kind of
Different
eras
waves,
so
yeah.
I was just curious if you had, I don't know,
no,
knew him or read.
I don't, but maybe some of the other people that have been here longer would,
Yeah.
yeah.
Okay. Cool.
See ya.
See ya.
Thanks.
Ask two questions for the lecture.
Yeah, sure.
Can I explain the indicator part, function part for the?
Indicator function is a function that's 1 or 0,
Okay.
and it's 1 whenever that expression is true.
Mhm.
So we've used this in a number of the homeworks, and
Okay.
we've used that notation before.
And this ratio is so the denominator would be.
The number of elements in that subset, the size of the subset.
Mhm. So this is between 0 and 1, right?
That's right, yeah. Yeah, that's each of these values. So like, let's say I have 2 classes, and let's say I have a total of n elements, and, 1/3 of them are in one class, 2/3 in the other. So here I would have, this would sum across all the 0 samples, and would count. Every time I find a 0 sample,
Mhm.
I add to my counter,
Mhm.
and then this divides by the total number of samples. So it just gives me the relative ratio of how many 0 samples are in SL. So how many, if k equals 0. If that makes sense.
Okay, so this SL is
SL is some subset. It's a subset I'm working with.
okay.
Okay, this is a subset, and I'm asking, within this subset, how many of the samples are k equal to k?
Okay.
So this is just the proportion of samples equal to k. So yeah, it's a number between 0 and 1.
Okay.
That's it.
And this is only for the classification, not the.
Right.
Okay. And another question is, can you explain why the decision tree tend to overfit these two?
Because, so one sign of overfitting is when you can perfectly predict all your training data. So that trees can do that. Another idea is, imagine that I change one sample in my training data. You could actually cause the entire tree to change, right? Like, because maybe like something happens at the root node and then everything changes.
Larger variance.
So yeah, so it's kind of like very small changes in the data can lead to very big changes in the predictor.
Oh, okay.
So like if you imagine doing an experiment over and over and over, every time you do the experiment, you might have a completely different tree. So that would lead to a large variance across experiments.
But if it's at the bottom of the tree, that will not.
It wouldn't affect as much, yeah.
Oh,
Right.
okay. And that's why we are using the random forest.
Yes, it helps. We want our weak learners to have low bias, but high variance. Yeah.
Okay.
It's interesting, so I don't know if you know, like sometimes at some fairs, they'll have like a big jar of marbles or something, and they ask the people in the audience to predict how many marbles are in the jar. Have you ever heard of this? Like you have a jar like this big, and this thing has, it's even hard to say, right? Like does it have 1,000 marbles, 10,000? You know,
So only ask people to predict the number of marbles
in the jar, yeah.
in the jar.
And they take like a, you know, everybody has a vote, and the winner, who gets closest, they get a prize, right? So this is like a thing that people do sometimes. What's very interesting is when you average all the predictions, it's very close to the truth. So it's like people are unbiased in their ability to predict.
Does this relate to the central limit theory?
I don't think so.
Okay.
Yeah, it just relates to a surprising fact that people are actually pretty unbiased predictors of this. But they have a high variance, right? Some people are
Right.
going to over, under predict, but like the reason that this works is because people are unbiased. Because if everyone was biased the wrong way, like if everyone under predicted, then the average would be under predicted.
Right.
So the fact that the average is actually accurate says that somehow we're unbiased.
That's
Yeah, it's pretty
amazing.
cool.
Okay, thank you.
Sure,
And I have a question about this week's homework.
yeah.
In number 2, we are given those two tensors. I think the second dimension of X tensor should indicate this channel number of input channels.
Yes.
Also, the weight, I call it weight tensor. The second dimension should also be Cin. But I expect those two numbers to be the same, but one is 10, one is 20.
So I think this is C in, C out, if I remember right. Is
Uh,
it C in, C out?
Because in lecture we are doing
C
this
out,
C
C
out,
in.
C in, so I was quite
Oh.
confused by those two.
Oh, well, there may be a typo then. Okay, because I changed a bunch of stuff.
Oh.
So it could be, yes, that these need to be swapped.
I
So
see.
thanks for letting me know. Yeah, they should be 2010.
Thank you.
Okay, thanks for letting me know.